Hey everyone, welcome back to another very exciting Unity VFX particle tutorial, and today is actually going to be a continuation of where we left off last time. Namely, we created this ParticleSeek component, a custom component for the Shuriken particle system, and what it really just did is enable the seek behavior on all the particle systems towards some target with whatever force we specified. So if you haven't checked out that video yet, please take a look at it. So in this tutorial, what we want to do is improve this component in every way possible. We want to make it look better in terms of the code, and we especially want it to perform better, which is why I've attached this optimized version here that we're going to be comparing it against. So let's do some preliminary checks, right? So all I've done with the scene is just made the particle system spread out its particles a bit more, just so it's easier to see the effect, and we can actually start comparing these two. So right now, if I play the scene, I have the profiler open. You can open that up from Window, Profiler. Okay, nothing's going on right now. We enable the ParticleSeek component, and we see that now late behavior is taking around, or we can see the ParticleSeek component is taking around anywhere from 8 to 7 to maybe, 8 milliseconds, and it has a bunch of stuff for the garbage collector to deal with, which is not so great, especially if when you compare it to the second one. And if I enable that one, you can see it's only taking about 2.5 milliseconds, which is, it's almost 3 times as fast as the previous components. So that's not a minor improvement. That's actually a significant change. So we're actually going to get started soon. One other thing I'd like to point out is that there was a bug in the previous script that's kind of difficult to notice. If I enable this, basically, and I play this, you'll see that, it's seeking towards the target like it should, but if I rotate it, it no longer does what it's supposed to do like it should, whereas the improved version, it'll handle that just fine. So I do want to thank Gurin from the Unity 3D subreddit for pointing that out. If he hadn't, or she hadn't, then I probably would never have gotten on to this. All right, so all I have right now is the ParticleSeek optimized 2 script that I've already created, and it's really just an exact duplicate of the ParticleSeek script, just so we can start modifying it. There's no change other than the name. First of all, let's do some aesthetics cleanup, okay? So we really don't need this. This is not going to improve the performance in any way, but it just, it's kind of in the way, and I don't like it. In terms of PS, we can actually just go ahead and name this particle system, and then replace every other reference to PS with actually saying particle system. Now again, this is not going to affect the performance, but in the current document I'm going to replace everything. It just does look nicer and it's easier to understand. Now you can see it's throwing out a warning saying hide inherited member, and that's just because in Unity 4, every game object just kept a reference to the particle system and light and a bunch of other stuff. But now in Unity 5, what you have to do, or as of Unity 5, you have to assign that manually by getting the component like we do. So all you have to really just do is, not a new, but throw a new in front of there, and it's all good. Other than that, I think we can get started. So we're going to go in order of the biggest offenders in terms of performance, and then we'll just work our way down to see how we can continue optimizing it. So let's disable the ParticleSeek, enable our ParticleSeek optimize 2 script. It's already, got everything filled in, and we'll hit play. So right now, the performance should be identical to the original script, right? You can see it's just about the same. And if we open it up, we can't see a lot of what's going on. So what we actually need to do is enable deep profiling. We'll let it reload the scripts. And now if we play it, it's going to be much slower, by the way, just because, it's going through the entire component. But we can actually see what's going on. So we've got 10,000 particles to work with. But I'm doing this 30,000 times, 10,000, 20,000 times. There's a bunch of this, and it's just slowing the whole thing down. Whereas in the optimized version, if I can actually manage to get this to stop, it's much better. You've got 10,000 particles, you've got 1 call per particle, basically, and it's just much faster overall. So we want to get it to this state. So if we go back to the ParticleSeek optimized 2, let's find out what's the worst one right now. So the biggest one is string memcopy. Now, we'll fix that right now. What happens is it's basically because I'm assigning back into the array, right? So although this is easier to type because you don't have to put in the array operator, it's not so great for performance. Let's take that out and then replace these with the actual particle position, like so. And now that we've done that, it should be fixed. So let's play again. So we're going to be doing this a lot. We're going to be going back and forth. between these two. What happened? Oh, I forgot this. We're going to be going back and forth, checking how it's improved and, whatnot. So that's going to be our basic cycle. So let's hit play. Check this out again. And you can see it's been fixed and it's already starting to improve itself. So it was about 40 before, it's 31 now. What else? Get normalized. So we do need to normalize this. That can't be avoided, but if we look at it, there is a way we can actually improve this. Because get normalize actually makes a call to vector3 normalize anyways. And after that, it's got to do what it's got to do. So we can write all this stuff out. I'm not sure how much of this gets fixed when the project is actually compiled into a build, but it's great for the editor anyways, just so it's easier to work with massive particle counts and whatnot. So we can see we've got a double call here. So instead of doing .normalize, we can instead just call vector3 normalize, and that way it's not using this to call this, and it just saves some time. So we can get rid of this right here, and instead just put vector3 .normalize in front. It's already in brackets, and it just takes in the one value, and then we should improve that. So let's take a note of this, 32 milliseconds. If we play it again, let's see what happens. So this is about 5.83. Should be 4 now. There you go. It's about 4, and it's about the same, maybe 30, 31. So it has improved a little bit. Next thing we can take a look at is this multiplication operation. So even though we have 10,000 particles, this is being called 20,000 times. Now the reason for that is right here. This is the only place we multiply in this entire script. We've got one multiplication call here, so that's 10,000, and then another one. So we looping through the 10,000 times the 2 multiplication, we got the 20,000 calls. So how can we improve this? Well, if we take a look at this, we'll actually also notice another thing. Time.delta time is also called about 10,000 times, okay, right here. And that's also taking up, some time to simulate. So what we can do is, one thing we can do to get rid of that is just, save the float outside of the for loop for time delta time. That's one way, and then multiply it. But either way, we still have those 2 multiplications. We can kill 2 birds with 1 stone here if we just pre-multiply the force and then multiply the direction to target. The force inside this loop isn't going to change. So we can actually just put force delta time as a variable we create up here, which is just force times time.delta time. And then instead of having these 2 multiplications, we can compress it into this one. Like so. So let's take a note of about a 30-second millisecond calculation time, and if we hit play, wait for it to compile, hit play, see what happens. Okay, so 29, 27, it has improved, we've gotten rid of that. What else can we fix? So the transform point, that's, oops, let me just pause this actually, because otherwise it's going to go all over the place. So this is basically unavoidable. Transform.get position. So we really don't need to get the position 10,000 times. We can just save it since it's only getting it from the same transform. So in here, in the local, it's doing, here we go, target position. So we can save target, the transform for it outside and the position, and just work off that. So what we can do is save the transform position, so the target position. So target position equals target position. And that way, we don't have to deal with that anymore. So let's hit play again. So it's about 28 milliseconds right now. Let's keep cutting away at that. Okay, so if we let's see what our benchmark is. So right now we had, about 20 something. We started at, I think, 40. Our benchmark is about 15. So we want to get it down to 15, right? So right now it's still sitting at 25 or so. And it's also really choppy, which is a problem. So let's fix that, and first of all, let's take a look at this, right? We've got all of these allocations. Let's fix that right now. So the reason for that is because every frame I'm allocating a new array to the size of the number of particles, and we don't have to do that. We can actually just move this array outside, maybe just throw it somewhere like there, and here. We don't have to constantly do this. What we can do instead is, let me just comment this out because I will be copying and pasting some of that later. We can check if, first of all, if the particles array has been assigned. If it hasn't, if it equals null, then we can assign it, right? So we can do this part right here. So that'll just get it initialized. That's the first thing. Okay. So that's fine. That's just the first one. But the other thing we need to check, or what we can do, is instead of making it to the size of the current particle count, we can just set it to the size of the max number of particles from the start, and then we don't have to worry about what the particle count is. So what we can do is we can just check the particles.length, and if it's less than the particle system dot main max particles, and then and only then assign it. So that way it'll assign it 1 on the first run, right? So assign it once on the first run, and then as long as max particles does not increase, then this should be fine. This will only be called once, and it won't be called over and over again every frame. And realistically, for Shuriken, you really never need to touch this value once you've set it, even before hitting play. So that's really good. So that way we'll know we always have enough space to accommodate the maximum potential particles in the array. So we hit this now, the garbage collector is at 0, and it's not as, randomly chopping around. It's still pretty bad, but it's an improvement. And actually, we probably should have fixed that first before anything else, because I think that was one of the worst things. But anyways, this is about the same. So let's see what we can fix next. So we've got the main module get simulation space. We've also got subtraction right over there, but I don't think we can change that. So we have get simulation space, which we can improve by saving the simulation space. We're also doing particle get main, right? So not only are we getting the main module over and over again, which is unnecessary because the main module can be saved even outside of the function call because it's not going to be changed. And the simulation space may be changed during playback, so that one can go outside of the for loop but still inside the function. So let's start off by first saving the main module. So we can save the main module right here outside because it's never going to change. So we can do particle system dot main module particle system main module. Okay, and we can assign it here because, like I said, it's never going to change. Right after we have the particle system, we can just store its main module instead of constantly getting it, because I'm assuming it's a property. Okay, and anywhere where we have particle system dot main, we can just replace it. So let's Control F, make sure it's matching the case, otherwise it'll also replace the original, and replace this with this in the current documents and make sure to match the whole thing. So replace all. Okay, and just remember this got replaced too, so we can just go back here and fix that up again. Or main, there we go. Okay, so that should again improve both of those things. We also need to save the simulation space actually before it improves both of those things. So I know beforehand that that's going to be useless and I'm going to have to change it again later. So what I'm going to do is fix the bug right now that we were having. So again, if you remember, the bug was based with rotation. And the reason that happens is because when I take the particle system, or the particle position in the system out of the simulation space of the particle system, put it to world position, and then I use that for calculations, and then later add that to velocity. The problem is the velocity is still used with the simulation space of the particle system, not world space. Now, it's not, used in world space. So that creates the conflict. What I can instead do to fix that is, instead of taking the particle system position out of the simulation space of the particle system, I can instead take the position of the target, which is in world space anyways, and then transform that into the simulation space of the particle system, which basically avoids all of this having to even be inside of the for loop. So that's a major improvement. So not only is it a bug fix, it's a major improvement. So we can take this out, and it's no longer the particle world position, it's actually the transform, or the target transform position. It's basically reversing what we were doing. So instead of operating on the particle, we operate on the target. So we have the target transform position. So first of all, it's not going to be anything. Okay. So let's target transform position. Let's replace all of these. This would go back to just being the per particle. And then this would be what we use instead. And other than that, for here, it'd be the same. So we'll just put this out. Now, obviously, this has some issues because this needs to be dot position. Okay, I think that's good. So target transform position, we actually have to play with this a little now. So simulation space equals, etc., etc. Also, I'm going to use a switch statement. This isn't so much of a performance increase, but it just looks nicer. So we can check the main module simulation space. Let's set this up. Oh, this keyboard is really a hassle. Okay, so if it's a case local, then do so-and-so, put in a break there, and copy and paste this, and if it's custom, then do so-and-so, and if it's world, then do so-and-so, and then finally we have a default, just in case, Unity decides to add something later, and then the user tries to change it, where, well, we don't need a break. What we're going to do is actually throw an exception. So this, I got to thank Gurun again, because this one, I didn't think I'd use it, but then I saw him use it, and I decided, hey, this looks cool, so thank you. So not supported, was it not supported exception? And we'll drop it down because it's going to be a long one. String.format unsupported simulation space. Also, switch statements and enumerations really go hand in hand anyway, so let's grab this parameter right here. Wait. Yes, comma, system dot get name. Want to know which one failed, so we get the type of the particle system simulation space right here. Main module, so particle system main module dot simulation space, and that'll just stop this entire script from finishing off. And I think we need another one here. Yep, that's good. Okay, so let's Control A, Control K after format. No real formatting issues anyways. And there we go. So let's just take this stuff out. So this should have been in local. This belongs in custom. This belongs in world. And then, of course, we have the default. So we can take this out. Now, let me just throw that there. Okay, so let's see. This should be the target transform or the target position. So this can be target dot position. This can be target position. The reason we're not saving the target position is because it's only going to execute one of these at a time. So it's not actually executing it 3 times, it's either executing this, or So that should actually fix our bug, and we can just go ahead and test that real quick. So if we rotate the particle system, it should continue to go towards the object, unlike before, where it wasn't. Oh, no, actually, we did something else wrong. What did we do? Oh, right, okay, so I actually forgot to change these to inverse transform. So before we were taking the particle system from local to world space, as you can see the description, right? So transform position from local to world space. Now we're taking the world space position of the target and transforming it to the local space of whatever reference transform we're using. In this case, the transform of the particle system. So we put inverse transform this time. And then it's the same thing. Okay, so let's play that now. Okay, you can see it's doing the same thing as before. Now if we rotate it, just let it play for a while so I can really confirm. And yeah, it's doing the exact same thing. So we can check the scene right here, right? It's working as it should. So let's stop that, go back here, and everything looks good. So let's go back to checking these calls right here. So we've already probably improved it significantly, right? So before it was like, what was it, 25 something? Now it's immediately been cut down to 15 already. So we're very close, I think, to finishing. Oh. So with those things out of the way, there's really no more optimizations to do. This is really good. It's basically the same as the optimize script. But the last thing I want to do is add the require component header attribute at the top, and this just means particle system. This just means that any game object that attaches to will automatically have a particle system attached to it, which is good because, you're going to be using it anyways. And if it already exists, it can't be removed. So if we want to test that out, all we have to do is create a new game object. Once it compiles, we can throw the script on and you'll see it'll automatically add a particle system like it should. And, then I can just drag the attractor and it'll work like it's supposed to. So also, I totally forgot, but this should actually be particle system main module.max particles. And if we want to save this up, because in some instances it might be called twice, we can just do that as int max particles equals this, and then we can just use max particles here and here. And that's about it. One final playback and we'll finish it off. So let's take a look at this. It's about 15 milliseconds compared to the optimized script. Again, about 15 milliseconds. And let's compare it to the original, 40 something milliseconds. So that is a huge improvement. We can take the deep profile off, let it reload scripts, and let's take a final look at it. Final look for the second time. 2 point something or other versus the original 7 or 8. So that is a huge improvement. All right, so that about wraps up the tutorial. Thanks for watching, guys. Let me know in the comments what you think, what you'd like to see next, and, subscribe. All right, bye. Oh.